All right, welcome to The Explainer. Today, we're diving into a world where the stakes are, honestly, unfathomably high. When you drive past one of those massive industrial chemical plants, it usually just looks quiet, right? Just a giant maze of pipes and towering columns silently doing their thing. But inside those steel walls, engineers are constantly managing this incredibly delicate balance of immense pressures, extreme temperatures, and highly volatile materials. It is literally a high-wire act of chemistry and physics. So today, we're going to unpack the brilliant, methodical, and totally life-saving engineering of safety and loss prevention in chemical process industries.
Here is our roadmap for today's explainer. We'll be looking at quantifying industrial hazards, the fire and explosion index, mapping the chemical process, the last line of defense, and finally, relief pressure thresholds. Okay, Section 1. Quantifying industrial hazards. How do we measure the unseen?
Now, in industrial chemical processing, we aren't exactly just mixing ingredients in a kitchen bowl. We're orchestrating violent chemical reactions on a massive, massive scale. And managing that requires completely removing any guesswork from the equation. Which brings us to a really fascinating question. How exactly do you measure a disaster before it even happens? How do you assign a tangible, hard number to an event that hasn't occurred yet, but could literally level a city block if it did? Well, to prevent total chaos, safety engineers need a highly systematic, ruthlessly mathematical approach to quantify danger.
Moving to Section 2, the fire and explosion index, our standard tool. So this is the standard tool that engineers use to translate abstract, catastrophic risks into hard, actionable data. Think of it like the ultimate grading rubric for potential disasters. What you're seeing is a section of the fire and explosion index form. Notice how it specifically breaks down general process hazards. It assigns these precise penalty factor ranges for things like exothermic chemical reactions, which, by the way, just means reactions that generate their own heat, or material handling and indoor process units. It's basically treating hazard assessment like a strict audit. The more complex or volatile your process is, the higher your penalty score gets.
Let's see how this actually builds up in a real-world scenario. Here we have a form populated for a nitric acid and ammonia plant. If you look at the top right, the basic material is listed as ammonia, and it's given this baseline material factor score of 4. From there, the engineers systematically go down the list, applying penalties based on the specific, ground-level realities of this plant's design. It's a sobering, really meticulous process of stacking up the inherent dangers.
Now, look closely at this specific penalty factor, 0.60. On the index we were just talking about, this penalty is assigned specifically for toxic materials. What's absolutely crucial to understand here is that toxicity isn't just about health and safety exposure. It's actually a mathematical multiplier for disaster probability. Think about it. If a pipe bursts and the material inside is highly toxic, the emergency response is instantly complicated, right? It makes an explosion or a fire far, far more likely to spiral completely out of control. So, here is how the math all tallies up. In this final calculation, the general process hazards factor, called F1, is multiplied by the special process hazards factor, F2. That gives us the unit hazards factor, F3. Then, that number is multiplied by our base material factor from earlier. The math on this specific plant yields a final fire and explosion index score of 21. And you guys, this single number dictates the safety spacing of the equipment, the type of fire protection required, and the level of automated shutdowns needed. It's the numerical foundation of the entire plant's safety philosophy.
Section 3. Mapping the chemical process. Visualizing the flow.
All right, now that we've calculated the mathematical danger of the materials we're working with, we need to actually visualize how these dangerous chemicals flow through the physical facility. Behold the piping and instrumentation diagram, or P&ID for short. To the untrained eye, sure, this looks like absolute alphabet soup, just a chaotic web of lines and overlapping acronyms. But to a chemical engineer, this is the nervous system of the plant. Every single line is a pipe. Every circle is a sensor, a transmitter, or a controller monitoring flow, temperature, and pressure. When safety engineers look at the schematic, they aren't just seeing how the plant runs normally, they're hunting for choke points. They want to know exactly where pressure could dangerously build up if, say, a pump fails or a valve gets stuck.
Let's act as a tour guide for a second and navigate that schematic by tracing just one critical path. We start with liquid ammonia drawn from storage. It's sent to a vaporizer to be converted into a gas, then forced into a compressor to drastically increase its pressure. From there, it's pushed into the main reactor, where the volatile magic actually happens. And finally, the byproducts head to a scrubber. Every single step here represents a massive jump in energy, temperature, and pressure. And at every step, the system is just begging for a mechanical failsafe. Which brings us to Section 4, the last line of defense, mechanical safeguards.
Because what happens when the computers crash? What happens when the power goes out? Those digital sensors fail, and the chemical pressure starts rising toward a catastrophic rupture. Well, we rely on mechanical interventions, like the relief valve. This is a safety device explicitly designed to protect a pressurized vessel or system during an overpressure event. It's a piece of hardware that acts entirely independent of any digital control system. When physics demands an exit, this valve provides it. It is quite literally the last line of defense standing between normal operations and an industrial disaster.
And notice the contrast in engineering approaches here. On one side, we have a conventional spring-loaded valve. It's beautifully simple. You have a massive, tightly coiled spring physically pushing a disc down to hold the pressure inside the tank. If the tank's pressure pushes up harder than the spring pushes down, boom, the valve opens. Pure brute force physics. But on the other side is a pilot-operated valve. This one's a bit more complex. It actually uses the system's own pressure to keep the main valve sealed tight, while a smaller pilot valve sits on top, monitoring the threshold. Once that set pressure is hit, the pilot valve vents, disrupting the seal and allowing the massive main valve to blast open.
But hey, engineering is all about alternatives, right? Like this fascinating buckling pen relief valve. Look at the rigid metal pen at the top of the closed mechanism. Instead of a spring compressing, this valve relies on Euler's law of structural columns. When the pressure hits an exact, mathematically precise threshold, that pen doesn't just bend, it catastrophically buckles and collapses. The valve instantly snaps completely open. It's a one-and-done, single-use component, but it provides a massive, immediate relief path when fractions of a second matter.
And that leads us to Section 5, relief pressure thresholds, calibrating the escape.
Because having these brilliant physical valves installed is really only half the battle. We have to calibrate exactly when they trigger. How do we calibrate that escape hatch? Well, here is the timeline of an overpressure event. Step 1. The plant is humming along at its normal operating point, comfortably 10% below the safety limit. Step 2. A blockage occurs. Pressure suddenly spikes to the set pressure, the absolute limit. Step 3. The relief valve experiences its initial pop. It starts venting. At this point, pressure is actually allowed to climb up to 10% over the limit to achieve the valve's full maximum relieving flow. And Step 4. The absolute nightmare scenario. A fire is raging outside the tank, boiling the chemicals inside. In a fire scenario, codes allow the pressure to climb up to 21% over the limit just to expel the rapidly expanding gases before the metal tank itself literally tears apart.
So the underlying concept to grasp here is that acronym we keep referencing, MAWP, the maximum allowable working pressure. This is definitely not a suggestion, folks. It is the absolute physical limit prescribed by the vessel's metallurgical design before intervention becomes mandatory. Every single calculation, every F&EI index score, and every spring calibration is entirely engineered around keeping the beast inside those pipes below this exact metric.
Which leaves us with one final, pretty provocative thought. We've mapped the hazards, we've calculated the risks, and we've designed the flow. But at the end of the day, when the power is completely cut, when the digital alarms go dead silent, and the pressure violently spikes, is a finely calibrated piece of metal really enough? Well, the modern world relies heavily on the fact that thanks to brilliant process safety engineering, the answer is almost always yes. Thank you so much for joining me on this explainer, and I'll catch you in the next one.